Hello there, Mr. Sutton here with the BC Calculus 710 Extra Practice number 1 solutions on alternating series test. For number 1, we're trying to determine whether this series converges or not. Now this you might recognize is the alternating harmonic series. We've got, if we plug in 1, we've got 1 over 1, and if we plug in 2, well that's going to be, let's see here, negative 1/2, then positive 1/3. So this is the alternating harmonic series, which is known to converge. For number 3, we're trying to figure out whether or not this series converges. Now the terms of this series are alternating. They are decreasing in absolute value as we go, and also the limit of the nth term is going to be 0. So because these terms alternate and decrease in absolute value to 0, we can say this converges by the alternating series test. For this one, we're trying to figure out if this series converges or diverges. Now we notice that we have an alternating series here, and it looks like our denominator is growing. So we can say this alternates and decreases in absolute value to 0. If you take the limit as n approaches infinity, this will go to 0. So that means that this is going to converge then by the alternating series test. For number 5, we're trying to figure out whether this series converges absolutely, conditionally, or not at all. So we can rewrite this as negative 1 to the n over n, because that's what's happening with cosine. As you go by 1, 2, 3, 4 pi, you're just going back and forth between 1 and negative 1 when you take the cosine of that. So to see if this converges absolutely, we take the absolute value of this series, which is just 1 over n, no alternation there. And this is actually the harmonic series, which we know diverges. So we're not going to be converging absolutely. Are we converging conditionally without the absolute value? Well, taking a look back at the original series, this is actually the alternating harmonic series, which is known to converge. So we can say that we are converging conditionally by the alternating series test. On this problem, I want to know if this series converges absolutely, conditionally, or diverges. So first thing I'm going to do is rewrite this in a form that's easier to work with. For one thing, this cosine n of pi, well, this is really just cosine of pi, cosine of 2 pi, cosine of 3 pi. So we're just flipping back and forth between negative and positive 1. So I'll rewrite this as negative 1 to the n in the numerator. Denominator, this is really n times n to the 1/2. So this is n to the 3/2 down there. So now let me see what I can do with this. To figure out if I'm converging absolutely or conditionally, let me first test this out without the alternating thrown in, basically with absolute value. So let me call this 1 over n to the 3/2. Now this is a p-series with a p-value of 3/2. Since that's larger than 1, this actually converges by the p-series. And because it converges with absolute value, we would say this converges absolutely by the p-series test. On this problem, we want to know which of these 3 series converges. So starting with the first one here, we see that we have an alternating series, and if you take the limit as n approaches infinity, you'll see that this term is going to 0. So we then have a series that is alternating and decreasing in absolute value to 0, which means this is going to converge by the alternating series test. Now that means anything that does not have option 1 in it can be ruled out, so B and C are gone. All right, let's check out this next one. Now this next one is a little bit tricky because of the way they wrote this fraction, but it's a little bit easier to look at if you think of this as 3/2 to the n over n, because that's basically what's going on here. So I'm going to try the limit on this one of 3/2 to the n over n, because I suspect this is not going to pass the nth term test. It looks like the numerator is growing faster. So as n approaches infinity, we do indeed have an exponential term with a base bigger than 1 versus a polynomial term. Exponential grows faster, so this goes to infinity, which significantly is not 0. So that means this fails the nth term test and diverges because of that. All right, so option 2 is out. That means that we can eliminate choice E, so it's either A or D. It all comes down to whether or not option number 3 converges. Now this is one of those where if you know the convergence of 1 over n ln of n, that's actually a pretty useful one to just know off the top of your head. You might not have enough to just prove it in a free response problem, but on a multiple choice it can save you a lot of time. If you did not know that this diverged, The only way to really prove this one is by using the integral test. So let's go ahead and do that. We know that this is a term that is, for n greater than or equal to 2, this is a term that's going to be continuous, decreasing, and positive, at least for n values of 2 or larger. So we can use our integral test and rewrite this as an infinite integral. So we can write limit as b approaches infinity, integral from 2 to b of 1 over n ln of n dn. And now to actually integrate this, I end up needing to use substitution by swapping out ln of n for u. So let me say u equals ln of n. So then du is going to be 1 over n dn. And I'm going to have to replace dn in here with a du. So let me multiply both sides by n to isolate the dn that I want to get rid of. I also need my limits of integration to be upgraded to u values. So if we have an n value of 2, that means I have a u value of ln of 2. N value of b gives me a u value of ln of b. Swapping it all back in now, I've got the limit as b approaches infinity of integral from ln of 2 to ln of b. dn has been replaced by n du, and we have an n times u downstairs. N's can cancel out, so this is just du over u. Now we can take the antiderivative since there's only u's left. This is going to be ln absolute value of u, evaluated from ln of 2 to ln of b as b approaches infinity, so a lot going on here. So this is now limit as b approaches infinity of ln of b. Still going to leave the absolute value around because we could still get a negative number out of here since we're taking ln of numbers that are smaller than ln of e. And then we've got, let's see, minus ln of 2. Now as b approaches infinity, ln of b goes to infinity, ln of infinity goes to infinity, so this whole thing goes to infinity, which means we're diverging by the integral test, which means that, yeah, option 3 is no good. So then it's just option 1, choice A. On this problem, we're looking for the interval of convergence for this series. Since it's not geometric, we use the ratio test to figure this out. So I've got the limit as n approaches infinity of absolute value of n plus 1th term, so that's 3x minus 2 to the n plus 1 over n plus 1, over the nth term, which is just this original summand here. Same change flip, I've got 3x minus 2 to the n plus 1 times n, and then in the denominator, I've got n plus 1 and 3x minus 2 to the n. 3x minus 2's can cancel out, leaving me with just a 3x minus 2 in the numerator and an n. Denominator is just going to have an n plus 1 now. As n approaches infinity, I can ignore this little plus 1, so the n's end up canceling, leaving me with just 3x minus 2 in the absolute value. We can set that less than 1. And now for the interval of convergence, I need to rewrite this without absolute value. So I have negative 1 less than 3x minus 2 less than positive 1. Add 2 to both sides. We've got a 1 minus, or less than 3x less than 3. Dividing all these things by 3, we've got 1/3 less than x less than 1. But we're not really sure if that's the true interval of convergence because we used ratio test, not geometric series test. So we need to test the endpoints. At an x equals 1/3, what's happening to our series? So that would be 3 times 1/3, which is 1, minus 2 is negative 1, so we would end up with negative 1 to the n over n. This is the alternating harmonic series, which is known to converge. Next, let's test out the endpoint 1. If I have 3 times 1, that's 3, minus 2 is 1, 1 to the n is just 1. So we have 1 over n, which is the harmonic series, which is known to diverge. So final interval of convergence, we have 1/3 less than or equal to x less than 1. On this problem, we want to find the interval of convergence for this series. Since this is not quite geometric because of this n down here, we have to use the ratio test. So I have limit as n approaches infinity of absolute value of n plus 1th version of this. So x minus 2 to the n plus 1, n plus 1, 3 to the n plus 1, all that craziness, divided by the nth term of this. And now let me do some same change flip magic here. I got x minus 2 to the n plus 1 times n times 3 to the n in the numerator. Denominator, I'm going to have this big expression times x minus 2 to the n. Let's see what we can cancel now. Can't really do anything with the n and the n plus 1 just yet, but let me cancel out a few things. 3 to the n and 3 to the n plus 1, subtracting the exponents, I have a 3 left downstairs. X minus 2's can cancel out to leave me with just one x minus 2 in the numerator. So when the dust settles, I have an n and an x minus 2 upstairs. Downstairs, I've got 3 and n plus 1. And now, as n approaches infinity, we can ignore this plus 1 next to the n. So we've essentially got n over 3n, which reduces to 1/3, and we also have this x minus 2 hanging around. So let me set this less than 1 for my interval of convergence. And before I turn this into those double inequalities, let me just multiply both sides by 3. So now for my interval of convergence, I can rewrite this as negative 3 less than x minus 2 less than 3. Adding 2 to every side here, I've got negative 1 less than x less than 5. But I'm not really sure about that because I have to test the endpoints here. Since we found this interval of convergence with ratio test, the endpoints are ambiguous. So if x equals negative 1, let's see what happens there. That would be negative 1 minus 2, so negative 3 to the n. Negative 3 to the n over 3 to the n is really just negative 1 to the n. We still have an n in the denominator. This ends up being the alternating harmonic series, which we know converges. Next, let's say that I have 5 for my x value. So 5 minus 2, that would be 3 to the n. Over this other 3 to the n is just going to cancel out. So that's just 1 over n when the dust settles. So this was at x equals 5. 1 over n is our series. That is the harmonic series, which we know diverges. So writing the final interval of convergence, I can say negative 1 less than or equal to x since we converged at negative 1. And then just less than 5 since we're diverging at 5. And this ends up being answer choice E. To figure out the interval of convergence on this one, we're going to have to use the ratio test because we do not have a geometric series. So I have limit as n approaches infinity of absolute value of x to the n plus 1 over square root of n plus 1, all of that over just the original nth term down here. Same change flip, we've got x to the n plus 1 times radical n in the numerator. Denominator, we have x to the n and radical n plus 1. I can cancel out these x terms here to leave me with just an x to the first power and a radical n in the numerator. This x to the n is completely gone. We just have radical n plus 1 in the denominator. Now, as n approaches infinity, we can ignore this plus 1. Square root of n over itself is just going to cancel. So we just end up with x then inside the absolute value. Setting that less than 1 to get our interval of convergence, we can rewrite this as negative 1 less than x less than positive 1. But we have to test out our endpoints because we're not really sure if we converge or not there. So at x equals negative 1, and by the way, let me put a little question mark here. There we go. At x equals negative 1 now, this is going to be negative 1 to the n over radical n. This is a series that is alternating, and because of this radical n here, it's decreasing in absolute value to 0, which means that this series is going to converge by the alternating series test. Next up, let's see what happens if we plug in positive 1. Well, that's just going to give me 1 to the n, which is just 1 over radical n. So at positive 1, we just have 1 over root n. Now this is a p-series with a p-value of 1/2. Since that's less than or equal to 1, we know this is going to diverge by the p-series test. So our final interval of convergence then, we've got negative 1 less than or equal to x, just less than 1. For this no calculator free response, we have this nth term of 1 over n ln of n for n greater than or equal to 3. And we're given this f function, which is basically this, but with x's. And they're telling us for x greater than or equal to 3, f is continuous, decreasing, and positive. Use the integral test to show that the series with this as our nth term diverges. Okay, well, they're pretty much telling you exactly what to do. We need the integral test. We've already been given the conditions for it. Again, for n greater than or equal to 3, we have a continuous, decreasing, positive function. So let's go ahead and just integrate this thing from, it'll have to be 3 to infinity. That's how we use the integral test on this. And we have to use a limit as well because this is an improper integral. So I have the limit as b approaches infinity of 3 to b dn over n ln of n. Now for this one, I'm going to have to use some u substitution because derivative of ln is 1 over n, and we see that in the problem here. So let me let u equal ln of n. So then du, which I'm going to have to swap in for the dn, is going to be 1 over n dn. So that means that n du is equivalent to dn, which means we can swap out that dn now for something better. We also need to mess with the limits of integration. If n is 3, let me say 3. There we go. Then that means that u is going to be ln of 3. And if n is b, u is going to be ln of that. Swapping everything back in, we have limit as b approaches infinity of the integral from ln of 3 to ln of b. And then we're going to have, instead of dn, we're going to have n du in the numerator. Downstairs, we're going to have n times u. N's are going to cancel, so that's just du over u. And now since I've only got u's left here and u values as well, I can take my antiderivative with respect to u, which is just going to be ln absolute value of u. Again, evaluated from ln of 3 to ln of b with b approaching infinity. Plugging in my limits now, I've got ln of b. Still going to leave that in absolute value, by the way. And then I have ln of absolute value, ln of 3, which I don't really need absolute value on, but I'll leave it there anyway. And then as b approaches infinity, this first term is going to infinity, which makes this whole thing go to infinity. So that means we are diverging with this integral, which means that our original series is going to diverge by the integral test. On this problem, they're giving us the infinite series negative 1 to the n plus 1 of this 1 over n ln of n expression here. And they gave us a few terms of this series just to really show us what they meant. Identify the properties that guarantee this series converges. Okay, well, we notice that we have a series that is alternating. That's a big tip-off here. And it's also, if you look at this, the denominator is getting bigger. And if you look at the nth term as n approaches infinity, this is really going to 0. So we're actually alternating and decreasing an absolute value to 0 for this series, which guarantees that this is going to converge by the alternating series test. Next part of the question, explain why the sum of this series is less than 1/3. So the key on this is that it's an alternating series. So the same conditions that guarantee this converges by the alternating series test also guarantee by the alternating series bound that the error is going to be less than the absolute value of the next term. Now you might wonder, well, what's going on with error? They didn't mention any kind of approximation or error in this problem. They just mentioned the sum of the whole series. Well, you can use this error expression in a unique kind of way, because error really just means the sum of the rest of the series that you didn't use. Well, let's say we wanted the whole series. What would be the next term if we wanted the whole series if we didn't use the whole series in an approximation? Why, it would be the first term. So we can say the whole series is less than the absolute value of the first term if we have this alternating series error-bound conditions met. Well, what is the first term? It's just this 1 over 3 ln of 3 expression. So the whole series is less than that. Now, significantly, 1 over 3 ln of 3, that's a larger denominator. Since ln of 3 is bigger than 1, because ln of e would be exactly 1, this is a larger denominator than in 1/3. So that means this is actually going to be less than the criteria they wanted us to meet here. This is less than the 1/3 they wanted us to beat. So that proves what they told us to prove here. For this last part of the problem, they want us to find the interval of convergence for this crazy looking series here. So this is something different than we've seen before. This is not a geometric series by any stretch of the imagination, so we need the ratio test to start this thing off. So I'm going to use limit as n approaches infinity of absolute value of n plus 1th term of this. So that's x minus 2 to the n plus 1, which is n plus 2. And then we've got n plus 1 times ln of n plus 1 below that. So that whole big nasty thing is the n plus 1th term. And then we have the nth term down here, which is just a carbon copy of what you have in the summation there. Next up, let's do same change flip and simplify this thing. So we've got x minus 2 to the n plus 2 and n ln of n in the numerator. In the denominator, we've got this n plus 1 ln of n plus 1 and x minus 1 to the n plus 1. I can reduce these x minus 2's by subtracting the exponents. That leaves us with just x minus 2 and n ln of n in the numerator. Denominator still has this n plus 1 ln of n plus 1 stuff. Now, as n approaches infinity, I can ignore these plus 1's that are next to the n's. So this essentially becomes n ln of n down here, which cancels neatly with the n ln of n upstairs, leaving us with just x minus 2. So I can set that less than 1. And now I can rewrite this without absolute value to get my interval of convergence by saying negative 1 less than x minus 2 less than 1. Add 2 everywhere. We've got 1 less than x less than 3. But I'll put a question mark because I still need to test my endpoints to see if I converge there. So at x equals 1, what does our series look like? We've got 1 minus 2, which is negative 1, to the n plus 1 over n ln of n. Now, this looks kind of familiar. In fact, we proved that this converged in part B using the alternating series test. So we've actually already proved this one converges. At x equals 3, what do we have? Well, that's going to be 3 minus 2 is 1 to the whatever is just going to be 1. So we have 1 over n ln of n. Now, it took a little bit longer, but we proved that this converged using the integral test in part A. So pulling all this together, we can write 1 less than or equal to x because we proved that 1 converged, less than 3 because we proved that 3 diverged, and this is our final interval of convergence.